Hello, welcome to my presentation. My name is Amir Hossein Hadian Rasano, and this is my pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. In this work, we have developed an extension of the Lévy Flight Model based on the racing accumulator framework, which is able to model multi-alternative decision tasks. During this presentation, first, I am going to talk about the Lévy Flight model and its limitations. Then, after mentioning the major features of the racing accumulator framework, our new model, which is based on the combination of the Lévy Flight model and racing accumulator framework, will be presented. I will also present the fitting results of our new model on a speed accuracy trade-off dataset. Okay, for about 2 decades, the dominant theory for explaining the underlying processes of making a decision in 2 alternative decision tasks was the drift diffusion model. In this model, there are 2 absorbing boundaries for correct and incorrect decisions. The process of information accumulation starts from a point between these 2 boundaries and then continues at a constant rate until reaching one of these 2 boundaries. One of the main assumptions of this model is that the accumulation process is noisy and the noise distribution is Gaussian. But recently, this assumption has been revised by some researchers. So the main idea of the Lévy Flight model is substituting the Gaussian normal noise of accumulation process in the drift diffusion model with a heavy tail distribution named stable distribution. Voss and his collaborators have shown that the Lévy Flight model can have better fitting performance on behavioral data in comparison with other alternative models. By considering the stable distribution as the noise distribution of the accumulation process, some sudden jumps have occurred during the accumulation process. Based on our previous findings, these jumps can reflect some psychological processes. Despite the advantages of the Lévy Flight model, it has some limitations too. The first one is that it cannot be used for multi-alternative and also one alternative decision tasks. On the other hand, it does not have an exact likelihood function, and it makes working with this model difficult even for 2 alternative cases. But racing accumulator framework provides a powerful and mathematically tractable framework for modeling multi-alternative decision tasks. In principle, this framework considers an accumulator for each option, and the accumulators work independently. The decision is made when one of the accumulators reaches the decision threshold A. So, by taking the same procedure as the Lévy Flight model, the raised Lévy Flight model can be obtained by substituting the Gaussian normal noise of each accumulator with a stable distribution. So, this model can be used for both one alternative or multi-alternative decision tasks. But what does happen for the likelihood function? The procedure of calculating the likelihood function for the racing accumulator models is so straightforward. So if we have the first passage time distribution and the cumulative distribution of the first passage time, the likelihood function can be obtained easily. Thus, our problem is finding the first passage time distribution of one accumulator. By applying a Fourier transformation on the accumulation process and using the central limit theorem and then taking an inverse Fourier transformation, this fractional differential equation is obtained. The solution of this fractional differential equation is the probability distribution of the location of the accumulator over time. So the survival probability of each accumulator is defined as the integration of the minus infinity to a of probability distribution with respect to x, where a is a threshold parameter. Then the first passage time distribution of each accumulator equals minus derivative of survival probability with respect to t, and the cumulative first passage time distribution is obtained by 1 minus survival probability. This fractional differential equation can be solved numerically or analytically, but we have used a finite difference schema for solving it. In order to test the performance of our model on behavioral data, we have fitted it on a speed accuracy trade-off dataset by Forstmann and her collaborators. In this experiment, 19 participants have taken part in a motion discrimination task with 3 different conditions: speed, accuracy, and neutral. In the speed condition, participants should only care about the speed of the response, and the accuracy is not important. In the accuracy condition, participants should only care about the accuracy of the response, and the speed is not important. In the neutral condition, participants should care about both speed and accuracy of the response. By fitting the proposed race-Lévy flight model on this data and comparing the obtained results with results of the race diffusion model, it is clear that the proposed race-Lévy flight model is better than the race diffusion model. And also it has a good fitting performance on behavioral data. As a conclusion, we developed a race-Lévy flight model which is applicable for multi-alternative decision tasks and also has a mathematically tractable procedure for obtaining the likelihood function. On the other hand, our new model performs better than the race diffusion model. This project is done under supervision of Dr. Jamal Amanullah with the collaboration of Dr. Amin Padash and Dr. Nathan Evans. I should appreciate them for their supports and helps. Thank you very much.